Hey everyone, and welcome back to Talk Tensors, the podcast that takes a deep dive into the world of machine learning research. Today we're tackling a paper that's, it's making waves in the field of multimodal large language models.
Yeah.
MLLMs.
That's right.
Yeah.
These models are becoming really important.
Yeah.
Because they can handle both text and images, makes them ideal for applications like customer service, or operations.
Yeah, exactly. Imagine talking to a chatbot that not only understands your words, but can also see a picture of, the problem you're having.
Right.
It's like having a virtual assistant who can actually see what you're talking about.
Yeah.
But there's a catch.
Right.
These models need a ton of data to work well.
And therein lies the problem.
Yeah.
How can we personalize these models for specific organizations without compromising the privacy of their data?
Oh, yeah, that's a good point.
Think about hospitals with patient records, banks with financial information, or even just, your own personal photo collection.
Yeah, it's a real balancing act.
Yeah.
Right.
Yeah.
We want the personalization, but we also need to protect sensitive information. So how does this paper propose to solve this problem?
Well, the paper we're looking at today is titled Privacy-Preserving Personalized Federated Prompt Learning for Multimodal Large Language Models.
Okay.
It's a mouthful, I know.
Yeah.
But it introduces a really interesting approach called DPFPL.
Okay, let's break that down.
Yeah.
DPFPL, what does that even stand for?
DPFPL stands for Differentially Private Federated Prompt Learning.
Okay.
Federated Prompt Learning, or FPL, is a way to train these models without having all the data in one central location.
Okay.
Instead, each organization keeps its data private and only shares a small prompt that helps the model learn.
So it's like giving each restaurant like a basic recipe, but they can add their own unique spice blend to make it their own.
You got it. That's a great analogy.
Okay.
Now, the DP part of DPFPL stands for differential privacy.
Okay.
This is a mathematical technique that adds noise to the data to protect individual data points.
Gotcha.
It's like adding a bit of static to a radio signal. You can still hear the music, but it's harder to pick out individual notes.
Interesting. So we're essentially adding this static to the prompts to protect the underlying data. But how does this actually work in practice?
Yeah.
I mean, wouldn't adding noise make the model less accurate?
Well, the paper dives into the technical details of how DPFPL balances privacy and accuracy. One of the key challenges they address is something called data heterogeneity.
Data heterogeneity.
Yeah.
That sounds intimidating.
Yeah, it's a bit of a jargony term, but it basically means that the data from different organizations might have different characteristics.
Okay.
Think of it like this.
Okay.
Imagine you're trying to train a model to recognize different types of flowers.
Right.
But the data you get from one organization might be mostly pictures of roses.
Okay.
While the data from another organization might be mostly pictures of lilies.
Okay, so the data from different organizations might be biased in different ways.
Right.
And this creates a problem for the model.
Right, exactly.
Yeah.
If the model is trained on data that is mostly roses, it might not be very good at recognizing lilies.
Right.
And vice versa.
Makes sense. So how does DPFPL address this challenge of data heterogeneity?
Well, remember how we talked about each organization having its own prompt?
Yeah.
In DPFPL, each organization actually learns two prompts.
Okay.
A global prompt that is shared with all the other organizations.
Okay.
And a local prompt that is kept private.
Okay, so the global prompt is like the basic recipe that all restaurants share.
Right.
And the local prompt is like the secret ingredient that makes each restaurant unique.
Precisely. Now to address data heterogeneity.
Yeah.
DPFPL uses a technique called low rank adaptation, or LoRA. LoRA.
Yeah.
Okay, you're gonna have to explain that one.
Sure. Think of the local prompt as a complex spice blend.
Okay.
LoRA breaks this spice blend down into two parts.
Okay.
A set of core ingredients.
Okay.
That are shared among all the restaurants.
Okay.
And a residual term.
Okay.
That captures the unique essence of each restaurant's blend.
Okay. I'm following so far. We've got the global prompt,
right,
the local prompt, and now this LoRa technique is breaking down the local prompt into core ingredients and a residual term.
Exactly.
But where does the differential privacy part come in?
That's where things get really clever.
DPFPL applies differential privacy in two ways.
Okay.
It applies global differential privacy to the global prompt, which is shared and aggregated on a central server.
Okay, so it's adding that that static we talked about earlier to the shared recipe, right?
Exactly.
But what about the local prompt?
That's where local differential privacy comes in.
Okay.
It's applied to the core ingredients of the local prompt,
right?
Which remain with each organization.
So it's like carefully masking the core ingredients of each restaurant's spice blend.
Yeah.
Even though they're being shared in a way.
Right.
This all seems very intricate.
Yeah.
I'm curious, how does adding noise to these different parts actually help to protect privacy?
That's a great question.
Yeah.
And it leads us right into how this approach effectively balances privacy and model performance.
Sounds like we're reaching the end of part 1. Don't worry, everyone. We'll be back in part 2 to explore how this delicate dance between privacy and performance actually plays out. See you then.
See you then. Welcome back to Talk Tensors. Before the break, we were just starting to get into the how DPFPL protects privacy while maintaining that model accuracy.
Right. We left off talking about how this system uses both global and local differential privacy to add noise to different parts of the model's prompts.
Exactly. It's this strategic addition of noise that's really key to DPFPL's success. By applying global differential privacy to the global prompt, which is, aggregated on a central server, we can make sure that no individual organization's data can be easily identified.
So it's like adding a layer of obfuscation to the overall recipe, making it harder to trace back to any specific restaurant's contribution.
Precisely. Now, you might be wondering, why not just apply global differential privacy to everything?
Yeah. Why bother with local differential privacy for the core ingredients of the local prompt?
There is. Remember, the goal is to balance privacy with personalization.
Right.
If we were to apply global differential privacy to the core ingredients, we would lose some of the unique flavors that make each restaurant special.
Ah, I see. So by using local differential privacy, we can protect those individual ingredients while still allowing them to contribute to the overall flavor profile.
Exactly. It's a delicate balancing act. And to make things even more interesting, the amount of noise added through differential privacy can actually impact the model's performance.
Okay. Now that's counterintuitive. I would think that adding noise would always make the model less accurate.
Well, it turns out that a little bit of noise can actually be beneficial.
Really?
Think of it like this.
Yeah.
Imagine you're trying to learn a new language.
Okay.
If you only ever hear perfectly spoken examples, you might struggle to understand people who speak with an accent or make minor grammatical errors.
So a little bit of noise can actually make the model more robust and better able to handle real-world data.
Exactly. In machine learning, this is often referred to as regularization.
Okay.
Adding a bit of noise can prevent the model from overfitting to the training data and help it generalize better to new unseen data.
Okay. That makes sense. But wouldn't adding too much noise still hurt the model's performance?
Absolutely. That's where the residual term comes in. Remember when we talked about LoRa breaking down the local prompt? We mentioned this residual term that captures the unique essence of each restaurant's spice blend.
Right. The leftover unique essence after extracting the core ingredients.
Exactly. This residual term helps to compensate for any loss of accuracy caused by the noise added through differential privacy.
So it's like a safety net that ensures that each restaurant's unique flavor still shines through, even after being, broken down and masked for privacy.
Precisely. It's this interplay between the core ingredients, the residual term, and the strategic addition of noise that makes DPFPL so effective.
This is all fascinating, but I'm curious to see how this theory actually plays out in practice. Did the researchers test this approach on real-world data sets?
They did, and the results are quite impressive. They tested DPFPL on several benchmark image classification data sets, and it consistently outperformed other federated learning approaches, even under strict privacy constraints.
Wow, that's That's really promising. What kind of data sets did they use?
They used a variety of data sets, including CFAR 100, Caltech 101, and Oxford PETS. These data sets are commonly used in machine learning research to evaluate the performance of image classification models.
Okay, so these are well-established data sets that allow for a fair comparison between different approaches. And you said that DPFPL consistently outperformed other methods.
Yes, even when they increase the level of privacy protection, which typically leads to a decrease in accuracy. In fact, they found that in some cases, increasing the privacy level actually led to a slight improvement in accuracy.
Wait, really? Adding more noise actually made the model better? That's incredible. How is that even possible?
It seems counterintuitive, but it goes back to that idea of regularization that we discussed earlier. By adding a bit more noise, they were essentially preventing the model from overfitting to the specific details of each organization's data, which allowed it to learn more generalizable features that were applicable across all the data sets.
So it's like adding a little bit of blur to a photo. Sometimes it actually enhances the image by smoothing out imperfections and highlighting the essential features.
That's a great analogy. Now, to really understand how the different components of DPFPL contribute to its performance, the researchers conducted what's known as an ablation study.
Ablation study?
Yeah.
What's that?
It's a systematic way of testing the importance of different components in a system.
Right.
They basically remove or ablate different parts of DPFPL, like the residual term, or the local differential privacy, and then they measure how it affects the overall performance.
So it's like a chef experimenting with a recipe.
Right.
They might remove one ingredient at a time to see how it affects the flavor of the dish.
Exactly. And what did they find when they ran this ablation study? Did it confirm their hypothesis about the importance of the residual term and the different types of differential privacy?
That's a great question, and one we'll pick up in part 3 of this deep dive. Don't go anywhere. Welcome back to Talk Tensors. Before the break, we were on the edge of our seats waiting to hear the results of that ablation study for DPFPL.
Right. Remember, the ablation study helps the researchers figure out which parts of this complex system are really doing the heavy lifting.
Right.
They essentially remove different components.
Right. One by one.
Yeah.
To see how it impacts that overall performance.
So it's like taking apart a clock to figure out which gears are essential for keeping time. Right. What did they learn about the inner workings of DPFPL?
Well, their findings confirm the importance of both the residual term and that strategic use of differential privacy.
Right.
When they removed the residual term, the model's performance suffered, particularly in terms of personalization.
So that unique essence really is crucial for preserving those individual flavors, even after, adding noise and extracting those core ingredients.
Exactly. It's like trying to bake a cake without the secret ingredient that makes it special.
Right.
You might have a decent cake, but it won't be the same.
And what about the differential privacy part? What happened when they experimented with removing or changing those elements? They found that the type and level of differential privacy used had a significant impact on both privacy and accuracy.
Okay.
When they removed differential privacy altogether, the model's accuracy improved, but of course at the expense of privacy.
Right, that makes sense. Yeah.
Yeah, it's a trade-off.
Yeah, more privacy typically means a bit less accuracy, and vice versa.
Exactly.
Yeah.
But what's really interesting is that they found that this trade-off wasn't always linear.
Right.
In some cases, increasing the level of privacy actually led to a slight improvement in accuracy.
Really? That seems counterintuitive.
Yeah.
How can adding more blur to the picture make it clearer?
It's all about finding that sweet spot where the noise helps to filter out irrelevant details, and allows the model to focus on the most important features.
Yeah.
Remember our language learning analogy.
Yeah.
Sometimes a little bit of noise can make you a more robust learner.
Right. It's like learning to understand different accents or dialects.
Right.
It might be confusing at first, but ultimately it makes you a better communicator.
Precisely. So this ablation study really highlights the delicate balance that DPFPL achieves between privacy and accuracy.
Right.
It's not just about adding noise randomly. It's about strategically applying different types of noise to different parts of the system.
So we've covered the technical details of DPFPL.
Right.
But let's step back for a moment and talk about the bigger picture.
Sure.
What are the real-world implications of this research? What does it mean for the future of machine learning?
Well, I think this research has the potential to be truly transformative. It
Yeah.
opens up exciting possibilities for developing personalized AI applications
Right.
in fields where privacy is paramount, like healthcare,
Right.
finance,
Yeah.
and education.
Okay, let's dive into some specific examples.
Yeah.
How could DPFPL revolutionize healthcare?
Imagine a world where hospitals can collaborate to train AI models
Right.
that can diagnose diseases earlier and more accurately, all while ensuring that that sensitive patient data never leaves the hospital.
That's incredible. It would be like having a global team of doctors
Right.
working together without ever having to share patient records.
Exactly. And it's not just about diagnosis.
Right.
DPFPL could also be used to develop personalized treatment plans, tailoring therapies to individual patients' needs and genetic profiles, all while protecting their privacy.
Okay, that's pretty mind-blowing.
Yeah.
What about finance? How could DPFPL change the way we manage our money?
Think about personalized financial advice.
Sure.
With DPFPL, banks could develop AI models that provide tailored financial recommendations based on individual customers' risk profiles, financial goals, spending habits.
So it's like having a personal financial advisor
Right.
who knows you inside and out,
Right.
but without ever actually seeing your bank statements.
Precisely. And because the data remains, private customers can have peace of mind knowing that their sensitive financial information is protected.
These are some really compelling examples.
Right.
And I imagine there are many other potential applications we haven't even thought of yet.
Absolutely. And that's what makes this research so exciting. It's
Oh.
not just about solving a specific problem. It's about opening up a whole new world of possibilities for developing privacy-preserving AI applications.
Speaking of exciting possibilities, it's time for our Novel Notions segment,
Right.
where we take the ideas presented in the paper and push them even further.
Yeah.
What fascinating thought experiment did this paper spark for you?
Given the success of DPFPL in balancing privacy and personalization for image classification, I can't help but wonder if a similar approach could be used for other types of data, like audio or
Okay.
even text.
That's a really interesting thought. Imagine being able to train personalized voice assistants that can learn from your speech patterns and preferences without ever sharing your raw audio data with anyone.
Right.
Yeah.
Or think about personalized language models that can adapt to your writing style and help you communicate more effectively, all while keeping your private messages and documents secure.
Those are some incredible possibilities. It seems like DPFPL could be the key to unlocking a future where AI is truly personalized and privacy preserving.
It's certainly a promising step in that direction. Of
Yeah.
course, there are still many challenges to overcome.
Right.
But this research lays a strong foundation for future innovation in the field of privacy-preserving machine learning.
Well said. And on that note, we wrap up another deep dive into the world of cutting-edge AI research.
It's been fun.
Thanks for joining us on Talk Tensors. We'll be back next week with another fascinating paper that's sure to get your neurons firing. Until then, keep those algorithms humming.